Hello and welcome. In this video, we're going to be starting integral calculus. This is going to be an introduction for integration. We're going to try to understand what do we mean by integration, how is it useful, and how to perform basic integration. So let's start by saying if we have a curve that looks like this, so this is some function f of x, okay, plotted on the y and x axes, and let's say we want to find the area, okay, under the curve. Area under the curve means the area between the curve and the x axis. So let's say we want to find the area under the curve from a, so a is here, or let's say a over here. So this is a and this is b. So we want to find this area over here under the curve. If this curve was something like a rectangular curve or a straight line, it would be easy. We would just multiply the width by the height. But the problem is that this is a curve. So how can we get an exact answer to the area under this curve? Well, one method is to try and approximate it. Okay, so try and see something that is close to the area of this curve. And how we can do that? By dividing this area into a bunch of rectangles. Let's say we're going to divide it into around 3 rectangles over here. So this is rectangle 1, rectangle 2, rectangle 3, and from here to here, this distance is called delta x. This is delta x. This is delta x. Delta x should be more or less equal, but for the sake of the demonstration, this is what we got. So what would be the area of from A to B is going to be the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3. So rectangle 1 is going to be, let's say it's this rectangle over here. Rectangle 2 is going to be this rectangle over here. Rectangle 3 is going to be this rectangle over here. So on rectangle area is basically length times width. So the width is delta x for all. The length, we can use the fact that this is a curve, and we can use the y value of the right boundary of our rectangle to get the width, the length of the rectangle. So let's say this is x1, this is x2, and this over here is x3. So the height of rectangle 1 is f of x1, which is the y value evaluated for this curve when x is 1. The value of width, so width of rectangle 2 is going to equal f of x2. And then we can multiply each width with the length to get the area for rectangle 1, rectangle 2, and rectangle 3. So when we calculate, we're gonna end up with these areas over here. And for rectangle 3, it's this area. So this is an approximation. Why is it an approximation? Because we can see that there are some extra bits, okay, like this bit over here, and there are some bits that we won't include, like this bits over here. So we have some extra values and some values that we don't account for, like this bit is also extra. So we'd expect the area to be larger than the actual area under the curve. However, this is just an approximation. So how can we make our approximation better? Let's try to do something like this. What if we try to increase the number of rectangles that we take? So we increase the number of rectangles. So basically, instead of taking only 3 rectangles, we can, let's just do that. This is B, and let's erase this. So what if we took more rectangles? Let's just erase these bits. Yeah. What if we took more rectangles? We can see that if we divide it into more areas, so basically imagine that these rectangles are more or less the same width, okay, and we get the area for each rectangle, okay, this is going to give us a better approximation, okay, so the area of each single rectangle is going to give us an approximation which is better for the actual area under the curve. So how to do that? We need to come up with the same thing. So this width over here is delta x, and the length of the rectangle is going to be f of xi. So let's say this is x1, x2, x3, and so on until we go to x of n. Okay, so this is the heights. So f of x1 is going to be this value over here, which we're going to read from the y axis, and this is going to be the height of the rectangle, which I can then multiply with delta x to give me the area of this rectangle. So area of rectangle 1 is going to be basically f of x1 multiply delta x, and then I will add to that f of x2 multiply delta x, okay, until I finish all of them, until I have f of xn multiply delta x. So something that I should notice here is that as the number of rectangles increase, my area approaches or equals the actual area under the curve, or I basically get a better approximation. So how can we get the exact approximation? We can think of this as if we take an infinite number of rectangles between A and B. So this is not a finite number anymore. We don't have like 20 rectangles, 100, a million rectangles. No, we have infinite number of rectangles. So let's see how we can do that. So let's say these are rectangles. These rectangles are infinite, and n approaches infinity. N is the final number of the rectangles. It's not 1 million, it's not 10 million, it's not 100 million, it's more than that. It's infinite number of rectangles. So we can write that as the area is going to equal f of xi multiply delta x, and we need to somehow sum all of these rectangles. So we will do a sum, okay, from where I equals 1 until n, right? So this is basically the area of the curve under the graph. It has the length part multiply the width. The length is the value, the y value of the curve evaluated at xi. Okay, so it's f of xi, and the width is super simple, it's delta x. So to make this exact, or to get the exact number of the area, we need to take a limit as n approaches infinity. So basically, this is how to get the exact area under the curve. Okay, so this is basically the idea of integration. Integration is a sum as well. Integration is also a sum, and integration, I can write it as integration from A to B, okay, of f of x multiply dx. And these two are exactly the same, and I'll show you how. This part over here is replaced with this S sign. This sign looks like an S. It's kind of an elongated S, which is basically a notion for sum. So this part over here is the same as this part, okay? And this part over here is the same as this part. And this part, which is delta x, okay, is the same as d of x. D of x is when delta x is infinitesimally small. It's super small. So this expression for area that we established from our rectangles over here could be written in this way, and this is basically the integration of f of x. So basically what I want you to know, which is the most important thing in this class, is that integration gives the area under a curve. So if I have a function and I integrate it, then the answer of this integration is basically a function of the area under the curve. So let's see how to do that for actual functions. So let's say we have a function y equals x squared plus 3x plus 4, let's say. Okay, so when we want to integrate this function, okay, we integrate this expression over here with respect to x. So the area is going to equal integration, okay, of x squared plus 3x plus 4 dx. So this is going to give me a function of area. So it's a general function of the area. Okay, so how do I integrate? Integration is very simple. If you remember differentiation, it was, if I wanted to differentiate x squared, is gonna be 2x the power times coefficient and then reduce the power by 1. So 2x power 1. Integration is kind of the opposite of that. So integration is going to be, first step is add 1 to the power and then 2 divide by new power. What does this mean? Let's see how we can do that. So x squared, I will need to add 1 to the power, so it becomes x cubed, and then divide by the new power, which is 3, so divide by 3. Same here, 3x means that it's 3x to the power of 1, so add 1 to the power, 3x power 2, and then divide by the new power. And then 4x, this is similar to 4x power 0. So if you want to add 1 to the power, it's going to be 4x power 1 divided by the new power, which is 1. Okay, and there is something that is super important whenever we have an integral that is indefinite, and we don't have a or b, we don't want to take integration for certain intervals. Okay, like over here we wanted particularly from a to b. However, here we're just trying to get a general function for the area. Okay, so if we don't have this, we need to add something that's called the constant of integration, which is c. We'll look into that later. However, all I want you to know is how to integrate the functions. Okay, how to go from here to here, from here to here, and so on. Okay, so this is basically the essence of integration. Integration gives the area under the curve. If I want to integrate a function, I will add the power by 1, add 1 to the power and divide by the new power. So let's take some examples to see how this works. All right, so let's say we have a function, let's say y is equal to 5x squared minus 8x plus 5, and we want to differentiate that, so that integrate that. So the integration is going to be integration of 5x squared minus 8x plus 5 dx. Okay, so again we take each term alone and we add 1 to the power and divide by the new power. So 5x, now 2 plus 1 is 3 over the new power, which is 3, minus 8x, 1 plus 1 is 2 over the new power, which is 2, plus any integration of a constant is basically 5 x, and we never forget the constant of integration, which is c. So our answer, if we simplify, is going to be 5 over 3 x cubed minus 8 divided 2 is 4 x squared plus 5x plus c. This constant of integration, lots of students forget it, so make sure to not forget to put the c at the end if it's an indefinite integral. Okay, so let's say we have a question like this. So integration of x squared plus 4 over x squared dx. We can rewrite that as x squared over x squared plus 4 over x squared dx. So we know that this is 1, and now we can rewrite this as integration of 1 plus 4 over x squared. We can write this as 4x power negative 2, because I know a power negative m is the same as 1 over a power m. So if we have an x power 2 in the denominator, we can put it up in the denominator and multiply the power by a negative 1 dx. Now let's do our integration. We know that integration of 1 is going to be 1x, or basically x, plus 4x power negative 2. So if we add 1 to negative 2, that is going to be negative 1, and then we divide by the new power, which is negative 1, and we never forget the constant of integration. So this could be rewritten as x minus 4 over x plus c. So this is the answer to this question. Let's take another example. Let's say we have integration of negative 6x cubed plus 9x squared plus 4x minus 3 into dx. Again, this is going to be negative 6x, 3 plus 1 is 4, over the new power, which is 4, plus 9x, 2 plus 1 is 3, and we divide by the new power, which is 3, plus 4, 1 plus 1 is 2, over the new power, and then we know that minus 3 is going to be minus 3x, and we never forget the c. To simplify that, negative 6 divided 4 is basically negative 3 over 2, x power 4, 9 over 3 is 3, we have an x cubed, 4 divided 2 is 2, x squared minus 3x plus c. Let's take another example. Let's say we have integration of square root of x plus 1 over 3 root x dx. So let's rewrite that. We didn't start integration yet, we're just rewriting into an integrable form, I'd say. So we know that square root x is the same as x power half, plus we have a 1 over 3, and then we have an x power half in the denominator. If I want to move it up, it's going to become x power negative 1 over 2 dx. Integrating that, I'm going to have x power a half plus 1 is 3 over 2, and then divide by the new power. So we divide by 3 over 2. Dividing by 3 over 2 is the same as multiplying the reciprocal of 3 over 2, so multiplying 2 over 3. So this is basically the same as multiplying 2 over 3. So it's going to be 2 over 3 x power 3 over 2, plus we have a 1 over 3, and then we have x power negative half plus 1, negative 0.5 plus 1 is 0.5, or half, and then we divide by half, which is the same as multiplying 2 over 1, or multiplying 2, and we never forget the c. So this is going to be 2 over 3 x power 3 over 2, plus 2 times 1 over 3 is 2 over 3 x power half plus c. So this is your answer right there. Let's take another example. Let's say we have integration of y squared cube root of y multiply cube root of y with respect to y, so dy. So first of all, I can rewrite this as integration of y squared multiply y power 1 over 3, because cube root is the same as power of a third. So we know that a power m multiply a power n is equal to a power m plus n. So when we have the same base, which is in this case y right now, and they're multiplied, we can join them together and add the powers. So we will have a 2 plus 1 over 3, which is 7 over 3, because we have 2 plus 1 over 3. We multiply 3 and 3 up top, so it's 6 over 3 plus 1 over 3, which is 7 over 3. So this is the integrable form that we rewrote this equation to make our integration easy. Now we perform our integration, so it's going to be y, and then 7 over 3, we add 1 to the power, so plus 1. So this one I can rewrite as 3 over 3, and adding 7 plus 3 is 10, and the denominator gets copied, so it's 10 over 3. So it's going to be y power 10 over 3, which is 7 over 3 plus 1. Divide 10 over 3 is the same as multiplying 3 over 10, and I have a plus c, so this is my integration answer over here. For the definite integrals, we're going to be looking at those in future videos, so please don't forget to subscribe to not miss any content. Okay, let's take another example. Let's say we have integration of 2t squared minus 1 all squared with respect to t. First, I can expand this, so it's going to be integration of the first squared, which is 4t. T squared to the power of 2 is going to be t to the power of 2 multiply 2, which is to the power of 4. And then first times second times 2. So 2t squared times negative 1, that is negative 2t squared, times 2 is negative 4t squared. And then the second squared, which is negative 1 squared, which is a positive 1 with respect to dt. Integrating that, I will have 4t power 5 over the new power, which is 5, minus 4t power 3 over the new power, which is 3, plus integration of 1t of 1 is basically 1t or t, and we have a plus c in our answer. Right. Let's say we have something like this, integration of d theta. So this is basically integration of 1 with respect to d theta, and we know integration of a constant is basically just the letter we're integrating with respect to. So this is going to be theta plus c, because integration of 1 with respect to theta is theta. Okay? So I hope this video was helpful. This video was a quick introduction to integrals and how to perform simple integration. We're going to be looking at other forms of integration and other techniques like integration by parts or substitution in the future videos. So please don't forget to like, subscribe, and if you have any suggestions or topics you want to discuss, comment down below. I hope this video was helpful. Thank you for watching.